Okay, so let's get this party started. Good morning, everyone. Well, at least it's morning here in Iceland. Thanks so much for joining us, for joining this webinar today. We're really excited about this event and what we're going to be showing here today. The Treble team has been working hard on developing some new and exciting things, which we'll be sharing here today. For those who aren't able to be here today, but still signed up, this thing is being recorded, so everyone will be sent a link to a recording of the event afterwards. Also, if you have to tune out after some time or something, don't worry about that. Then you can see it afterwards. And we have scheduled this to be an hour, but we have a lot of exciting things that we want to show you. So I will try to go a bit fast so I can get through everything. There's a chance that we might go a few minutes over, but we'll try not to go too far over. But as mentioned, you'll get the recording afterwards. So what I'm going to show here today is, first of all, I'm just going to give a bit of an intro to Treble the company, and then the platform, the sound simulation platform that we are building, in case someone is new to Treble here today. Then move over to showing some new features and improvements to the product that we've been building, in particular, new ways to look at results, so surface style receivers or heat maps and color maps, the ability to analyze results just in a completely different way than what we had before. Some nice new additions to our Oralizer, such as being able to put in your own sounds, and some performance improvements as well. We've been working hard on making our solvers faster and have made very good progress on that front as well. We will be introducing a new approach to scattering modeling in our platform very soon. I'll tell you about that as well. And then we're also stepping up our support functionality, so having live chat support so you can immediately get help with anything relating to Treble. After that, I'll go over to showing some new validation cases. So we've also been doing a lot of measurements and studies where we're sort of analyzing the performance and accuracy of our simulation tool, and with some very exciting results on that front that I want to share with you as well. Okay, this is kind of the new things that are coming, or are coming very soon, or have been pushed already. Then after this part, I will talk more about the future, so the coming months, what's on the roadmap for Treble there. Many exciting things I can tell you, so I'm looking forward to tell you about that. And in relation to that, I want to also give you what I call here a sneak peek into some of the things that we're developing, showcase a couple of prototypes. These things are by no means ready right now. These are beta versions or prototypes, but still maybe give some insights into what will be coming in the fall from Treble. And finally, after that, open up the floor for some questions and answers. So I hope it all makes sense. I hope you're all as excited as I am about this. So Treble, the company, was founded in 2020, but actually its roots go back to several years of academic research prior to that time, mostly out of DTU in Copenhagen. And we're a team of around 30 people now, developing new advanced technology for simulating and working with sound and acoustics. Our team is like maybe 75–80% R&D, and of which maybe 50–50 software development talent and acoustics and audio experts. And the platform that we are building, we often talk about it as a platform of virtual sound, meaning it's a piece of software that has functionality relating to sound simulation on the one hand, and sound rendering on the other hand, the ability to listen to the simulation. And this kind of technology has use cases in various different industries and fields. But here to begin with, we've been mostly focusing on building design, but are sort of also have some plans for expanding that further into the future. And I'll talk a little bit about that here today. The core of Treble, our core technology, is our simulation technology, which is a new approach to doing acoustic simulations, which combines a wave-based algorithm for low mid-frequency modeling and geometrical acoustics for high-frequency modeling. This approach allows people to do more accurate acoustic simulations than what has been possible to date. And well, the idea of combining wave simulations and geometrical acoustic simulations is maybe not brand new. It's been researched for quite a few years, but it's never really sort of found its way to practice because the wave-based part has always been so computationally intensive. But we developed an accelerated wave-based algorithm that is much, much faster than what's been available on the market to date, making it possible to do wave simulations at very practical run times, even in large spaces. So in smaller spaces, you can actually do a fully wave-based simulation. In large spaces, you would do a hybrid approach where you would cover the low mid frequencies wave-based and geometrical acoustics for the high frequencies. Now, as mentioned, I'll be showing all kinds of benchmarks and validation cases that we've been doing a bit later in the presentation. So then I'll also give a bit more detailed insights into these two algorithms and how they work and so on. Okay, then this core, this simulation technology, which is all residing in the cloud, essentially we're building two interfaces to this core technology. The first interface, our first product, is a graphic user interface simulation product, a web-based tool. This is what we launched on March 1st and what I'll mostly be talking about here today. Currently mostly tailored towards architectural acoustics, but with some ideas of expanding the applicability of it in the future. But we have been working on a new product, which is essentially a programmatic interface to the cloud-based simulation technology, which has use cases, for example, in synthetic audio data generation, advanced acoustic analysis, and so on. And I'll briefly talk about this and show a prototype of this as a part of the webinar. This is being launched later in the fall, mostly focusing on this part and the new features that we've been building here. So let's dive into that. First, brief overview of the product and then the new features. So this is a simulation tool tailored for room acoustic simulations. And we're trying to introduce a new and hopefully better way of doing that. And what we are really trying to bring to the table, you guys be the judge of whether we're successful or not in doing that. But what we're really trying to do is essentially three things. We're trying to introduce more accuracy in room acoustic simulations so that people can be more confident in their results. We can reduce risk. We can reduce over design and things like that by having a very accurate simulation technology. And that's all thanks to this simulation technology, the core technology I was mentioning earlier. Combining that then with a very strong emphasis on trying to make the whole workflow with working with acoustics and simulations better, trying to integrate directly into 3D modeling tools, trying to have the whole user experience and user interface as smooth as possible, really exploiting the power of the cloud so you can do many simulations simultaneously and things like this just to overall make the workflow better. And finally, because we can simulate sound in a very accurate manner, we can also do very authentic oralizations. And we're also trying to just make oralizations a bit more fun, essentially, more interactive, and so on. A couple more words on each part here. So the accuracy is due to this combination of wave-based modeling for low and mid frequencies. In that frequency range, we have a lot of wave phenomena such as diffraction and interference and so on, which is inherently captured by wave-based simulations. Also, we're very proud of our geometrical acoustics high-frequency simulation engine, which is a phased engine, or pressure-based engine, which has been shown to improve accuracy as well. And this is new in the world of acoustics. We also offer the capabilities of modeling surfaces, which obviously have a huge impact on the acoustics of rooms in a more precise manner than what's been done to date. So modeling them in terms of the surface impedance and not just the energy-based absorption coefficients. And this all means that complex acoustic phenomena such as diffraction and interference is inherently modeled. And again, benchmarks coming a bit later in the presentation. The workflow, so right now we are live linked to SketchUp. So the connection between Treble and SketchUp is something that we're trying to make as smooth as possible. We have everything residing in the cloud. It can be run from any device and so on. But we're also working very hard on making this even better. For example, enabling a connection over to BIM tools, which I'll be demoing a prototype of here later today. Oralizations, being able to both see the model and hear it at the same time, being able to interact with the design, being able to move around, move the head, and share these kind of oralizations in an easy way. This is also something that we are emphasizing. Okay, so this was, oh yeah, one more comment I had here. There's been some research which kind of evaluated the perceptual quality of oralizations using either only geometrical acoustics models or this kind of hybrid approach where we combine wave and geometrical acoustics. And there was a very strong preference for these kind of hybrid oralizations in terms of perceived realism. Okay, this was the overview of the product, maybe something that you've heard me say before, but now the new stuff comes. So the first thing that I wanted to show you is these surface receivers and results view overhaul. So being able to analyze sound, across space and acoustic parameters, and just a more convenient way of looking at results and so on. So I'm going to switch from the PowerPoint here over to the web application and just showcase this. So it's still I'm here on our development branch. We'll be pushing this feature live next week. So let me show you here one example. I have this lecture hall here, which I'm going to go into. Which I've already imported a live link from SketchUp. And I'm going to create a Zoom window here. I'm going to create a simulation, but putting in these kind of surface style receivers. And then I'm going to show you how we look at results in a new way. So I'll just create a new simulation here. My pool simulation. I'm going to assign some materials. I'm just going to do this really fast. I have some results that I've already computed for more realistic materials. But just to show you something here. Throw in source somewhere in the model. Then now, if you're familiar with Treble from before, you will see a difference in that we can now define both point receivers and surface receivers. So point receivers are as before. Just kind of put that somewhere in the model. But then we can define surface receivers. I'm going to define one here. Something like this. I'll move it here to the center of the room. I can change the size of it, maybe 20 here. Length 20 as well. You can see it will sort of automatically clip the plane when it goes out of bounds from the room. I can move this surface receiver as I want in the space. I can tilt it, things like that. So maybe just to 45 degrees. Any way I want in the space. I can have many surface receivers. Sure, I'll put another one somewhere here. This maybe doesn't make a lot of sense to have it like this, but just showing that, I can kind of freely put receivers into the model and then analyze results kind of across this receiver. And as mentioned, I've already just run, for the sake of time, I've already run a couple of simulations in this space. So let me show you what these kind of results can look like. So here, in this case, I defined 3 plane or surface receivers. One here sort of across the stage in the sort of lower audience area. One here kind of more in this sort of sloped part of the auditorium. And then one sort of section through, so we can see that as well. Now, I assigned some materials here, some plastic chairs, gypsum board here on the back wall here. The ceiling is a acoustic ceiling, floor, parquet, the micro perforated panels here on the wall with some light absorption, and a stage floor. Now, here you can see the definition. I also put some point receivers and some surface receivers. I ran this up to 350 hertz wave-based. So that's probably very sufficient to capture most of the wave phenomena in this room. And then the rest was geometrical acoustics. And if we look at the results here, now we're going into the new revised results view. So the kind of main difference we will see here is that we have now introduced 3 different view types of results. So we have here the model view, which is where we start, report view, and the surface receivers view. The model view is basically a way to be able to see both the acoustic parameters, or let's say the graphs and numbers results from the simulation, but also see the model at the same time. So you can see, what receiver am I looking at here in space. And I can also look at these kind of plots, energy decay, impulse response, frequency response, and so on. I can compare some different results, for example, different receivers, and look at all the acoustic parameters we offer as before. Okay, going over to the report view, that's just sort of an emphasis on the graphs. So removing the model view, so we can see more details at the same time. For example, looking at the energy decay and the acoustic parameters at the same time. And we can, look at this for different frequencies, of course, these plots here, the energy decay curves, and so on. But then maybe the most new exciting thing is then to switch over to the surface receivers view, where I can see the different acoustic parameters vary across the space. We can see here it starts on the sound strength. I can select which frequency I'm looking at, going from low to high frequencies. I can control the scale here. I want to, for example, to be able to compare different simulations and have always the same scale, something like this. And I can look at some different acoustic parameters. For example, the reverberation time. Note here, because it's a wave simulation, then we're actually capturing the modal behavior of the space pretty well. So we'll see quite a bit of variation in the reverberation time across space at low frequencies. I can also look at the STI. Look at that as a function of the background noise in the room. Something like this. I can, by the way, maybe let's go back to this. I can also look at the results either interpolated or sort of more pixelated directly as they come from the solvers. So that's sort of in a nutshell this new results overhaul and the grid receivers. And this kind of introduces some very powerful capabilities to analyze the acoustics of spaces, also analyze kind of modal behavior and things like that. In terms of outlook on this feature, for example, being able to then animate sound fields across these surface receivers is something that we'll be developing in the coming months. Okay, I'm going to go back to the PowerPoint here. Next thing on the agenda is an improvement of the Oralizer, being able to input any sound into the Oralizer, and we've also done some performance improvements of it. We're not done with performance improvements. We'll continue improving it further so you can have more and more sources and more complex rooms and everything, but we've done some already. And let me just go directly back here to this model, and now I'm going to do an oralization. So I'll exit the result view and go into the oralization view. And here I can select sound from our library of sounds. As this was what we could do before. Select this jazz recording here. First play the anechoic recording. Maybe I'll change the look of the model to be a bit more realistic. And then I'm going to jump into the room and listen to how this sounds in the room. I can move the head in real time and the binaural audio updates in real time. I'm not sure it comes through binaural here over Zoom, but at least it does here on my end. I can pull in different simulations to compare. So this is the same room with some different material configurations, more reverberant. Now, in addition to having this kind of large library of sounds that come with the product, which is also ever growing, I can also import any sound that I want into here. I'm going to import here Immigrant Song by Led Zeppelin. As I'm sure all of you know, that's a song written about Iceland, actually, after Led Zeppelin visited and played a gig here in Reykjavik in 1970. So let's hear how Immigrant Song, well, let's first hear it directly as it is on the recording, and then we can hear it in the space. All right, so this is an example of putting in your own sounds into the Oralizer. I think I would definitely prefer this type of material configuration if I were at the Led Zeppelin concert in this room. Okay, moving on, more things to show. Accelerated solvers. So we are just about to push a change for our wave-based solver, which speeds it up about 25% across the board. That's very nice, of course. We've completely revamped our image source algorithm, which is what models early reflections at higher frequencies. So converting it to an accelerated beam tracing algorithm that makes it possible to run much higher reflection orders and just at much higher speed. And then the late ray tracing or ray radiosity method that we use at high frequencies has also been sped up substantially. This was very needed for the grid receivers because now we have hundreds of receivers in the space as opposed to just having a few. And we've done lots of benchmarks to analyze the performance of this and see, the speed up depends a little bit on the complexity of the model and how long of an IR you have and everything and so on. But let me just show you one example. So we're here dealing with a relatively complex concert hall model. Simulated that with grid receivers, so some 500 receivers across the space, simulated wave-based, the first 2 octave bands, and then geometrical acoustics above that. And before our performance improvements, we could only really run this up to second order reflection order of the image source method, and it still took around four hours to run with all these receivers. So the geometrical acoustics algorithm was the one that was holding it back so much. The wave-based one was just around 10 minutes, maybe or so. But now with this improvement, we run it up to third order reflection order in the image source method, and the time is drastically reduced for all these receivers. So very nice performance improvement, but we're of course nowhere done. So we continue improving and speeding things up as we go along. Okay, scattering, again, a feature that we're pushing very soon, just in the coming couple of weeks. So up until now, what we have been enabling is a single value input of scattering. So you put in one value. This is only used by the geometrical acoustics algorithm, so high frequency modeling. You put in one value, and that value is then extrapolated to a sort of S-shaped curve for kind of different frequency, different scattering at different frequencies. And this is sort of, one could argue, is sort of the industry standard approach to modeling scattering and room acoustic modeling today. This is a very nice approach, I would say, but we will continue allowing for that, but we will also offer now users the ability to input their own scattering coefficients at different frequencies if they want to experiment or do more detailed analyses of the influence of scattering on the resulting room acoustics. And this is possible because the Treble GA algorithm actually simulates or traces rays for each octave band, which is not what all other acoustic simulation tools do. They more sort of simulate just one set of rays and then sort of do some tweaks to kind of adjust to different frequencies. But because we do it in this way, then we can actually solve or tune the scattering coefficients for all octave bands. All right. Not a new feature, but a new thing we're doing, live chat support. So we really want to give our users the absolute best possible support and service while they're using our product. So we've established or put live here a live chat support, so you can kind of just chat with us directly and immediately get a response from our team of experts. It's open from 9 in the morning to 5 in the afternoon here at Iceland time. That means that For people in Europe, it's kind of open more or less all day, except maybe early in the morning. And for people in the US, North America, it's open in the morning at least. If you are outside these hours, the chat is still there, and you can send us a message, and we actually reply very quickly to that too. You can, of course, also just drop us an email, reach out to us like that if you want. Let me just show you. So this is already live on our website now, and then we'll be pushing it live into the platform, into the tool as well very soon. So there will be a chat window here. But let me just quickly show you here on the website. So the chat pops up here. I can just immediately start chatting. Hello. See if someone picks it up. I'm asked to input my email. I don't have to do it, but it's nice. Then we kind of see your previous chats and so on. So it kind of can help with some of the correspondence. And I'll just write to, for example, hi, where do I get the SketchUp plugin for Treble, as an example. And then Diana here's on the other end. Ooh, she's quick to respond and has, all the answers that I need. This is a way to get more and better support when using Treble. Okay, that was the live chat. So these are sort of the new features that we've been pushing or are pushing just these days. Now let's switch gears a little bit and talk about some of these validation cases that we have been doing. So I want to show you actually quite a bit, 5 cases in total, and they're all, I think, at least the acoustics nerd in me thinks, they're all super interesting. First is sort of a rather controlled scenario, diffraction around the barrier. Then we have 3 room acoustic simulation cases where we're comparing measurements and simulations. And finally, a bit of a different type of a validation case, which is more audio signal processing trained on room acoustic simulation data from Treble. So let's just dive into it. So diffraction is kind of the main phenomena that wave-based methods model very well and is very prominent in reality, but geometrical acoustics methods sort of in general struggle a bit with that. There are some approaches to try to model it in an approximate way in geometrical acoustics, but fundamentally it's challenging to model. And diffraction is essentially the phenomenon of sound waves bending around obstacles. So for example, a very classic example is an open plan office with partitions where you have sound bending around obstacles, bending around those partitions. Another example is noise barriers alongside roads, for example. Furnishing in rooms introduces a lot of diffraction, seat dip effect in concert halls and so on, same phenomena. This is a case taken from the benchmark for room acoustic simulations. That's a public database of all kinds of measurements and controlled scenarios which people can use to benchmark acoustic simulation methods. Here we have a loudspeaker and a source which is behind this barrier, and a receiver which is behind the barrier, and we simulate the frequency response between the source and the receiver. And sound, there's no direct sound, but there is sound diffracted around the barrier to the receiver. We've done several benchmarks from this database, but I'm just showing this one here today because it's relatively new for us. And here we see 2 simulation results. So the measurement is the blue curve, and then we see simulations with a wave-based simulation up to around 2 kilohertz. And then another one, which is geometrical acoustics simulation. In this particular case, using a method or a tool called Raven, which is a public open source. I think it's open source, at least a sort of academic geometrical acoustics solver coming from Aachen University. A very advanced geometrical acoustics algorithm. And as we see here, wave-based simulation captures the frequency response quite well. Of course, not perfectly, but there's also, for example, at low frequencies, more uncertainty in the measurements and so on. But in general, the trend is captured very well by the simulation, whereas geometrical acoustics algorithm doesn't really model this very well. Okay, next case, a small room study that we've done here at Treble. Here we're actually we tried to do a full bandwidth wave simulation, so no geometrical acoustics. And we modeled a directional sound source, a Yamaha loudspeaker, and we had some different absorption or an absorbing material kind of placed in different spots in the room, but also some, for example, hard parallel surfaces as well. So this is a relatively tricky model to simulate, even though it looks rather simple. But we have still rather controlled scenarios. We, for example, measured the surface impedance of this porous absorber. So we have pretty good material input data into the simulation. We measured a bunch of different source receiver combinations. For the receiver, we measured both the mono room impulse response and the binaural impulse response using a KEMAR mannequin. And overall, we were very pleased with the results. So this is one example of a mono impulse response for given source receiver combo, where we compare the measurements and simulations. And we see that the simulation captures the early reflections very well. And so the overall trend of the impulse response is also modeled very nicely. If we look at the frequency response, we see that the modal behavior at low to mid frequencies is captured quite well in the simulation. And also the sort of high frequency trend, for example, due to the directive sound source in the wave simulation is captured very well. Energy decay curves, pretty much spot on here. Kind of remembering also that we have pretty good material input data here. So we can get very good energy decay estimates. And resulting room acoustic parameters, this is T20 and early decay times also captured well. Note, for example, this pretty interesting behavior here. Because the absorber is kind of essentially more effective as we go higher in frequencies, but actually the reverb time is not really following that trend exactly. If you would do a Sabine estimate of this room, then you would see a reverb time that looks something like this. But in reality, because we have some parallel surfaces where the sort of two-dimensional sound field still lingers in the room, then we get an increase in reverb time at mid frequencies before decaying down again as well. And this is essentially, I would say, impossible, or at least very difficult to simulate in geometrical acoustics, but something that wave-based methods capture quite well. These are then the binaural room impulse responses. So going through our spatial audio, so both kind of spatial audio sound field pickup in the room in the simulation using a virtual microphone array, and then encoding that to high order ambisonics and decoding down to binaural signals. And these look very similar to the real measured thing. And frequency responses of the binaural signals as well. Okay, another benchmark, round robin study. So this is a space that was measured some years ago, and the authors of this round robin study also provide the model of the space. They provide the absorption and scattering coefficients of the different surfaces as well. And then many different simulation tools have tried to simulate this space and compare against the measurements. Here we see results. So this is the T20, oh, sorry, I wrote the T20. It's the T30 reverberation time at different frequencies for all the different source receiver combinations considered. And we see three curves. We see a black line, which is the measured reverberation time. We see this light blue color, which is the simulation from Treble. And then we see here the dark green one, which is the average of all the other simulation tools that participated in the round robin some years ago when this took place. And overall, we see here so we ran a hybrid simulation here up to and including the 500 hertz octoband wave-based, and then geometrical acoustics at high frequencies above that. And we see here for the lower frequencies, these two bands are wave-based. We see a very good match in most cases with the measurements, and overall a better match compared to the other simulation tools. There's one outlier here, which is not matching very well, but otherwise, I would say a really good match between measurement and simulation. For the higher frequencies, we're not spot on, but we're still closer to the measured curves compared to the average of the other simulation tools available. This is the same, but showing the early decay time instead of the T30 reverberation time. And I would say the trend is more or less exactly the same as well. So kind of great match at lower frequencies, improved match at higher frequencies. And then this is just one source receiver combo showing the full bandwidth results. Again, same story. great match at lower frequencies, improved match at higher frequencies as well. Okay, another somewhat similar case to what I showed earlier, but still slightly different. So here we have an even more sort of exaggerated non-uniformity of absorption in a room, and it's also a small room, so tricky to simulate. So we have one surface which is covered with a porous absorber, and the remaining surfaces are all reflecting. And what we'll see in these types of rooms is a very double decay, energy decay, because the sound field that's kind of facing the absorber will be absorbed very fast, whereas the sound fields that kind of lingers between the parallel surfaces will live very long. And these kind of grazing incidence waves that are kind of passing by this absorber will be absorbed very slowly as well in reality. And then it's interesting to look at the results here. So this is T20 reverberation time. There we tried with two different absorber types here on the wall. And we see in the measurement, again, this kind of somewhat counterintuitive trend that even though the absorber is more effective as frequency increases, then actually the reverberation time is almost shortest here at low frequencies because the room is rather small compared to the mid frequency and high frequencies. We simulated wave-based up to 1 kilohertz and then geometrical acoustics above that. And then we compare also to another geometrical acoustics tool available on the market. And this trend here of this very big increase in reverberation at mid frequencies due to this non-uniformity is captured pretty well in the simulation, not perfectly, but pretty well. And also the high frequencies are captured quite well with our phased angle-dependent geometrical acoustics algorithm. So a kind of new way, or one could argue at least that this is then showing that wave-based simulation is a kind of new way to model complex and challenging acoustic scenarios in a better way than before. This is early decay for the two absorbers as well. Okay. Final validation or research finding, a bit different from the other ones. So here, this is work that's will be presented at Forum Acousticum in the fall. The authors here, coming out of DTU, that what they were doing is they were training a machine learning algorithm to do blind room estimation. That is to take a measured impulse response or a measured room transfer function, and from that infer the size of the room and what the absorption properties of the surfaces of the room are. And they were just doing this for a shoebox room. And what they compared here was training this machine learning algorithm on wave-based simulation data or geometrical acoustic simulation data. So let me try to illustrate a bit here. So this part here above is the training phase. So they trained two machine learning models. The first one, they fed wave-based simulated transfer functions in shoebox rooms, along with the size of the room and the absorption coefficients at all the 6 surfaces that comprise the shoebox room at low frequencies. So this was only done at lower frequencies. They did the same, then trained another model, but using transfer functions simulated with geometrical acoustics. So fed in geometrical acoustics transfer functions and the size of the room and the absorption properties of the room. And then the model learns to map from a transfer function to these properties here. And then after training these two models, they took real-world measured transfer functions in shoebox rooms, where they also knew the absorption properties of the room, fed them to these models and analyzed how good the models were at predicting the size of the room and the absorption properties of the room. They found overall that both models were sort of comparably good at estimating the size of the room. Maybe the wave-based one was slightly better, but marginally. But the wave-based model was much better at predicting the absorption properties of the room. And that stands to reason because wave-based transfer function will simply be much closer to real-world transfer functions compared to the ones simulated with geometrical acoustics, especially here at lower frequencies. So this is one plot out of their paper, showing the error in absorption estimate for some different configurations, like absorber just on one wall or many walls, things like that. for the model trained with geometrical acoustics and model trained with wave-based. And they found overall that the errors in the geometrical acoustics model was twice as large as the error of the wave-based trained model. All right. Again, switching gears and now talking about what lies ahead here at Treble. So we've actually put out a public roadmap on our website now, so you can see what we're working on. This will be a living document. Things might change and so on, but this is at least the current thinking of what we are planning to do. So let me go through the coming months and sort of give the sort of high level overview of what's coming. So we just now are pushing these surface receivers and result overall and some other smaller improvements, which I just told you about. In September, we want to push the ability to simulate open plan office parameters, and that kind of allow users to have more control of the background noise when doing STI calculations. In October, we're planning to push the ability to import generic 3D models, so not just linking with SketchUp. So, for example, importing TXF files. How am I doing on time? Okay, time is flying. October, a big improvement in source modeling, so having a large library of directional point sources and the ability to import directional point sources as well. This is kind of version 1 of our source modeling capabilities. We will certainly continue working on improving those further, being able to model line arrays, surface sources, and so on, being able to import various types of sound sources, having a very large database. We're in dialogue with many of the big loudspeaker manufacturers and so on. So we really want to kind of adapt this tool to be great for pro audio sound simulations as well. But this is the starting point coming in October. And then the API, which I will give a sneak peek of in a second, is being launched on October 15th. Collaborative features is something we're really excited about. For example, being able to create a shareable oralization. So you set up an oralization with some different design options and things like that. Then you click create link, and then you can send that link to someone who can then listen and experience the oralization on the other end. Also being able to share projects with colleagues, kind of a Google Docs style collaboration on doing acoustic simulations, shared material libraries across organizations and things like that. BIM to Treble, also something I want to give a sneak peek of in a second. So kind of having an automatic way of going from BIM models to acoustic simulation models. Version 1 of this will be pushed here in Q4. Sound field animation, as previously mentioned, also coming. Transmission modeling, being able to model how sound propagates from one space to another. That's also coming later this year. And then in the start of the new year, a new version of the API with more features, a material generator, so we can specify your own detailed buildup of a material and compute the surface impedance, which is then used in the simulation. A live link plugin with Rhino, 6 degree of freedom oralization and VR integration, so you can move around the space more freely when you're oralizing, and then a Revit plugin a bit into 2024 as well. So these are some of the high-level things that are coming from Treble. And as mentioned, in relation to that, I want to show you 2 prototypes now. Saying again, these are things that are not fully matured in any way, any shape or form, but still hopefully give some insights into what we're working on. So the first one is this BIM to Treble thing. And as I'm sure many of you are familiar with, BIM models, this is kind of the industry standard way of doing building design and building models. But unfortunately, these types of models don't tend to be very well suited for acoustic simulations. They contain a lot of geometric details. They're not kind of watertight or just too many details, too many imperfections to be running simulations. So people who work with acoustics and building design, they spend a lot of their time, as I'm sure many of you are familiar with, cleaning up models, redrawing models from scratch and things like that to make them suited for sound simulation. And what we're really trying to do is to reduce this work effort so people can actually spend their time on the acoustics and not on sort of 3D modeling preparation. What version 1, this thing we'll be putting out later in the year can do is that you can import BIM models as an IFC file into Treble. It will do automatic space picking, meaning sort of cells, picking out different spaces that comprise the building, turning those into simulatable acoustic models with some automatic geometry simplification. So it should be ready to go for an acoustic simulation. You can, of course, then pull the model into SketchUp if you want to make some tweaks or change some things, but most of the time we're hoping that this will work well. Version 1 launched in Q4. So let me try and show you a current prototype where I'll import an IFC file and quickly simulate it and oralize it. So I'm going to go here to my local branch. This is just a prototype, and I'm going to click this button here, import IFC model or IFC spaces. I'll call it test IFC model. Blah, blah. And I will find my model here. It's a relatively basic BIM model still, but hopefully showcases something that we're working towards. And now it takes a few seconds to do this because it's not optimized at all in any way yet. But I'm just going to go here in my little debug tool and see that it got started at least. It is started. That's good. And while we wait, I can show you the model here in Revit. So as mentioned, not the most complicated BIM model, but still it has some details which might be tricky to deal with right off the bat. For example, you have some details here in the staircase. You have maybe not perfect matching between this window frame and the wall. You have thickness of these walls, which you don't really need. You just need the kind of inner surfaces of a room when you're doing acoustic simulations. This is a coupled space here between the first and second floor, and details around the doors and things like this. This BIM model has been divided into different spaces, as is typically done with BIM models. And what the algorithm is doing here behind the scenes while I'm talking here is it's kind of extracting these different spaces and making them simulatable for acoustics. And one thing to note, for example, is that, as I previously mentioned, this kind of large space here between the first and second floor is coupled, so there's an opening between. So even if it's defined as two spaces in the BIM model, then we want this as a single model for doing acoustic simulations. That's what the algorithm does. Okay, there's of course a roof here on top as well. I've just hidden that for viewing the model. Let's see how we're doing on the import. Says completed. So let's take a look and refresh here. So now here, this IFC model has been imported into Treble and it's been split up into the different spaces as previously mentioned. But note that the coupled space has been joined into one space as we would want for an acoustic simulation. And then I'll just enter one of these models, one of these spaces. I'll take the studio space here. It's a relatively simple space. I'll create a simulation. Again, just assign some simple materials, something like this. Throw in a source, receiver. And because it's not perfectly watertight, then we can only do geometrical acoustic simulations at the moment on this, but we're working on kind of automatically ensuring watertightness. But I can basically start right away an acoustic simulation. It takes a few seconds to run, and then I can do an oralization. So the goal is to be able to go from an even more complex model like this and into being able to look at results and oralize in just a few seconds, really. And you can see here that, this space has been cut out quite nicely from the BIM model. Okay, it's just about to finish. I just want to hear it. So be sure that it really went through. Here we go. Oralizer. Put some sound on. House music, why not? And we're in the space oralized. So still lots of exciting things to develop further, but prototype showing the sort of vision where we're headed with this thing. Hopefully this is of value to someone. Okay, the last thing of the presentation is a prototype for a beta version of this API product that we'll be launching a bit later. So the use cases here is it's essentially a programmatic interface to our simulation technology, tailored mostly for data generation. So you can simulate thousands of different scenarios easily and extract high fidelity acoustic data and use that for training, for example, speech enhancement or blind room estimation or source separation and things like that. So it's a Python-based interface to the simulation technology. Indeed, synthetic audio data generation, also just advanced acoustic simulations. We're exposing a lot of more controls and so on here in the API. So it can very well also be useful for building design purposes as well, doing parametric sweeps, for example, across some different boundary conditions and things like that. Also, some people might be interested in integrating our simulation technology into their software products, and this enables that in an easy way. And a key component of this, as with everything that Treble makes, is that it's all built in the cloud. So we can indeed be generating large data sets and simulating thousands of rooms in parallel to get results very quickly. I want to show you, again, a beta prototype of this and walk you through setting up a single simulation and then simulating 1,000 rooms. Takes about 3-4 minutes. Then we switch over to Q&A. Sorry for going a bit over time here. So I will go here. So this is what's called a Jupyter notebook. It's basically a Python code with some nice comments around it. And I'm going to, as mentioned, set up a single simulation and run that, and then set up 1,000 simulations and run that as well. So the first thing I need to do when using this API is that I just need to log in, fetching some credentials here. And then I'll import the Treble SDK or API product. After that, I create a project. That's kind of the sort of foundation of the hierarchy in the API, that you have a project and that contains a lot of simulations and so on that you have set up. So I'll just quickly create my little project here. And then what I want to do is I want to generate the geometry. And we have some different ways of approaching this. One is that we will have a very large database of geometries that come with the tool. Thousands of meeting rooms, thousands of open plan offices, thousands of restaurants, thousands of living rooms, etc., that have all kinds of furnishing and details that you can fetch and use for data generation. But you can also import your own 3D models, or you can programmatically generate some simple geometries as well. For example, an L-shaped room or something like that. But right now, I'm just going to fetch from our database all rooms that have a tag meeting room. And it so happens that there are 1,000 meeting rooms in our database right now. I can visualize the rooms. I'll just pick one and showcase it here. And we see, it has a table, chairs, TV, some windows and stuff like that. It has some metadata like labeling and positions of chairs and things like that can be useful for source and receiver assignment, for example. I can also print the metadata. So we see here, for example, the positions of the chairs and the layers in the model and so on. Or fetch the surface layers here. Okay, then I'm going to create a simulation just using one of these meeting rooms. I want my receiver to be on the center of the table of this meeting room, and I want it to be like a DRTF, device-related transfer function receiver. So basically a way to model a microphone array or device, just like we model HRTFs and do binaural rendering, but here with a microphone array. So I import some SOFA file, which contains the DRTF. This can be either simulated using Treble or measured in an anechoic chamber. And I place this receiver here at the center of the table. I use very high order ambisonics encoding when capturing the sound field above the table and kind of mixing that with the DRTF. So now my receiver has been placed on the table. Then I want to put some sound sources into the room. So we will again have a large database of sound source types. Right now, the database is very small because it's just a beta still, but we have some directional speech directivities as well as some loudspeakers. And here I'm just going to loop through all the chairs in the room and place a sound source a bit above the chair, which has the directivity of a talker and in a random orientation. Something like this. And assigning materials. There are many ways to go about this. One approach which we show here is that we fetch some different materials from our material categories out of the big material database that Treble has. And then we're sort of randomly putting some materials on these different layers in the model. And another way it could, for example, be just to specify reverberation time, and then the platform or the API would assign some realistic meeting room materials to fulfill that reverberation time roughly. I'll do it like this. We can validate that the setup is all right. So for showing that, I'm going to put a receiver into the model which is outside the room. I'll do that here. Create the simulation, so assigning all these different settings that I've been setting, as well as the crossover frequency and the impulse response length. That, and then I can ask it to validate whether everything's okay, and it will notify me. Sorry, 1 second. It will notify me that there is a receiver here which is in an invalid position, so it's not a valid simulation yet. So we can take a look at that. We see indeed here the receiver is outside the room. So I can simply ask it to remove all invalid receivers, and then my simulation is validated. And then now my simulation is ready. I've defined the geometry, sources, receivers, materials. So I'm good to go. As the settings of the simulation as well. I can estimate how long it's going to take. 0.02 hours, but it's essentially 4 simulations that are run because there are 4 sources. So the compute token cost is 4 times the time it takes. And I can start the simulation. It takes a few seconds here. This is being optimized, of course. And now that it's started, I can check the progress of it. And it says in progress, it's sort of being spun up. And as we go along, see percentage progress of this simulation. So that was an example of setting up one simulation from a programmatic Python interface as opposed to a graphic user interface. But maybe if I just wanted to do one simulation, then I could just as well have done it in the web application. But if I want to do some parametric sweep or simulate a lot of rooms and things like that, then that becomes very intractable in a graphic user interface. So let me show you here how I would go about simulating 1,000 meeting rooms. So it's actually very similar to what I just did. I'll create a new project called 1,000 meeting rooms. Again, I've already fetched this list of meeting rooms from before. Now I just create a for loop, which loops through each meeting room, places a receiver just like we did at the center of the table, places sources, directional speech sources above each chair in a random orientation, and randomly assigns materials at the different layers of the model from our material database, and kind of creates a simulation for each of these. This just takes no time to run. Now I've defined 1,000 simulations in 0.1 second. I can create the simulation, the sort of big simulation for all these different rooms that are defined. It takes a few seconds to run. Typically around 20 seconds. Let's see. Again, something that we're obviously working on and optimizing further. All right, and I can estimate how long this whole thing is going to take. And it's telling me here it takes about 5 minutes to simulate 1,000 meeting rooms, complex meeting rooms with several sources, several sources, one receiver device, wave based up to 1 kilohertz, and geometrical acoustics above that. And then I would have a very large database of room impulse, device-specific room impulse responses, high fidelity impulse responses, which I could use further for some downstream processing. All right, I've been talking a lot here, but this was all I wanted to show you today. Thank you so much for listening. Now I'm going to open the floor for questions. So I have here, I can see here on Zoom, I have already received some questions, which is great. So please don't hesitate to send in questions if you have anything here in the Q&A chat. Let me see here. Some people complimenting the new results view. That's fantastic. Thank you for that. Someone's asking if the recording is going to be available. Yes, you will be sent the recording after the event. Then we have a question here from Volker, who's asking, do you think Treble could be an alternative to ease to simulate professional PA systems? Can you use GLL speaker data? Fantastic question. We're definitely working towards this to be an alternative to ease for pro audio PA system modeling. There's kind of two aspects to it. One is just to develop the core technology to be able to simulate line arrays and things like that from a technical perspective. We're working on that, making great progress. For example, being able to do also wave-based modeling of that means more precisions in the simulation. For example, optimizing subwoofer arrays and things like that, which is really hard to do with ray tracing style simulations like EASE does. And the other aspect is the input data, all these loudspeaker data files and so on. GLL is a proprietary format. We're not sure that we can actually support that. So what we are we're exploring different ways of how we go about this. But I can say now that we will do our very best to enable either easy import of existing loudspeaker data, but we're also in dialogue with many of the big loudspeaker manufacturers to try to get these loudspeaker data compatible with Treble. So we're working on it, hopefully be able to present something some few months down the road. Thank you for the good question. I have another compliment here. Our support is awesome. That's good to hear. And that the future roadmap sounds good. Thank you so much, Philip, for that. So here's another question. So at the moment, it is only possible to import an IFC model into Treble and then use it to simulate in Treble, but not possible to export the model again and use simulation data for something in BIM. Great question. Wouldn't that be great if we could have a BIM model, link it to Treble, do the acoustic simulation, and then get results back into BIM? This is indeed something that's of great interest to us. I think sort of integrating acoustics more into BIM modeling is the ultimate goal here for sure. Just like nowadays you have, HVAC and structural and electricity and all these things, which are kind of really integrated into the BIM process. But acoustics is always just kind of on the side somehow. That's our long-term vision. To begin with, there will be more this one-way coupling where you have your BIM model, you can very quickly analyze the acoustics of it. But this two-way coupling of going back to BIM is something that we will try to enable as time goes on. Great suggestion. Another question here, is it possible to build an own model in Treble without SketchUp? So at the moment, we're only supporting SketchUp, but we are soon enabling, for example, DXF import. So you can, any 3D modeling tool can really export a DXF file, and then you can import that into Treble directly. The API also opens up the opportunity to kind of programmatically create geometries in a simple way in Treble, which you could simulate. So these are kind of the approaches that we're enabling in the near term. So either DXF import, IFC import, or this kind of programmatic definition of a geometry. Having some sort of 3D geometry CAD tool in Treble, where you can draw your own model and so on. We're not working on that at the moment, but some people have asked for it, so it's definitely something we will consider. So thanks for that. Peter asks, can I use own stereo sound files as input for the Oralizer or only mono sources? So the sources are mono in the Oralization. You can input stereo files, but then it will just merge into a single channel and play that back. So if you wanted to have a stereo experience, what I would recommend, for example, if you're simulating a studio and want to have like oralized 2 loudspeakers in the studio, then I would recommend splitting the stereo file up into 2 mono files, place 2 sources in the simulation for 2 loudspeakers, and put the left and right channel on those 2 and oralize it like that. Then you would get a real spatial experience in Oralization. Here's a question from Jacopo. By open plan office enhancement, do you mean the ISO 3382-3 standard method? Yes, that's exactly what we're referring to. So, the privacy, distance, the speech decay rate, and these parameters, that's the first ones we will be adding. There's also another recent standard. Now I'm a bit not up to speed on all the latest developments, but we will also be, I don't remember the name of that one, unfortunately, but I think there are some interesting parameters in that one too. So we'll definitely explore it. But the first ones are indeed these kind of ISO 3382-3 that are coming in September. Okay, so thanks for the good question. Another question here. Thanks for the presentation. We find the software quite intriguing, and it would be interesting for us to utilize Treble for current and future projects. That's great to hear. Some inquiries. Currently, is it feasible to utilize commercially available speakers for simulation purposes, taking into account factors such as the frequency response, directivity, and power potential? Indeed, as previously discussed, we are working towards enabling this. The first thing that we will enable in October is this CLF file, a common loudspeaker format import, which has frequency response, directivity, and sound power. So you can model directional point sources with that. At the same time, in discussions with loudspeaker manufacturers to get their data into our platform or create some sort of standard file format that can be used for that. So definitely working on that, and some nice steps toward that being introduced in October when the CLF comes. At present, can geometries in STL format be imported? Not currently, but when we enable this generic geometry import, then DXF will be supported. And I'm pretty sure that enabling STL or step files is also then supported. Maybe some Treble people are now scratching their heads and I'm saying something wrong, but I'm pretty sure that should be supported around the same time. Can moving sources be modeled for the diffraction of a barrier? That's indeed something that would be really cool to be able to do. We're not actively working on it right now, but it is on our longer term roadmap to support moving sources as well. Can a source be positioned outside a building to simulate the noise inside? That's coming with this transmission modeling, which was, where did we put it on the roadmap? Was it Q4 that we want to introduce at least sort of the first version of transmission modeling? So you could indeed have a sound source outside and inside. And then the final question here, some great questions from this person, this anonymous attendee. Is it possible to simulate curved geometries like half cylinders, semi-cylinders using Treble? Yes, absolutely. That's one of the things we pride ourselves on being able to do, is to handle complex geometries really well. Especially the wave-based simulation can do really complex detailed geometries very well. I hope that answers the questions. Okay, Christoph here asks, are the materials in the benchmark simulations fitted to the measurement, either GA or wave-based simulation, in any way? Because the absorption coefficients are most of the time the most uncertain input values. That is 100% true. The sort of Achilles heel of room acoustic simulations is the boundary input data. And there's a lot of uncertainty associated with the input data. And the good old sort of garbage in, garbage out applies here, as in any simulation. You need, even if you have this kind of very advanced simulation machinery that Treble is offering, then you need to be very mindful of what input data, both material properties and the geometry that you're putting in, to get good results out. In terms of these benchmarks that we have done, let me cover them one by one. So there are no really kind of absorption properties in this first diffraction around the barrier. It's just a rigid barrier. So that's not really a factor in this particular one. In this one, we have essentially two types of material properties. So it's a relatively simple room or sort of controlled scenario in terms of material properties. We measured the surface impedance of this porous absorber and used that as an input in the simulation. And then we used the database absorption properties for the concrete walls here in this room. And there was also a door and some things which we use sort of database values for. The impedance measurement is only valid for a limited frequency range, like, I don't know, 400 hertz to 2 kilohertz or something like that. So we kind of use the material model to extrapolate that to higher and lower frequencies. So it's a pretty well established materials here, no tuning that took place or anything like that. The round robin case, then the absorption properties and scattering properties are provided by the providers of the round robin, so we did not tune that in any way. Same here as for the other small room. We measured the surface impedance of this, and no, I'm sorry. We had from the manufacturer the flow resistivity of these absorbers, so we could use a porous material model to get the surface impedance based on that, and that's what we used in these simulations here. And again, some database value for the concrete walls, no fitting as such. So that's kind of these benchmarks that we showed here. No kind of tuning or fitting per se took place. Just either quality measured input data or database values. But the notion, I completely agree with that. That the input data is so important, and it's a lot of uncertainty with that. Also, just measuring absorption is really difficult. Okay, Dirk asks, in the first example, the number of rays was 5,000. With the ray reduction because of diffuse rain up to 50%, isn't 5,000 rays a very, very low value and not promising accurate results? So with this radiosity diffuse rain method that we're using for the late reverb tail modeling at higher frequencies, we have found that sort of ray ranges in, let's say, 3,000 to 10,000 rays gives very sufficient results in most cases, even complex geometries. Because every reflection of a ray actually creates a hit to the receiver, and you don't need that many rays to create a lot of reflections towards the receiver for this late part of the reflection modeling. So we've done some convergence studies where we have some different rooms and we simulate them for 1,000, 2,000, 3,000, 10,000 rays. And we see that the sort of parameter values and things like that start to stabilize around this, 5,000 to 10,000 rays, something like 3,000 to 10,000, depending on the room. But of course, it's possible to go higher to be, more sure of the quality of the results. And right now we're capped at 25,000 rays in treble, but with these kind of nice speed ups that we've been making for the GA solver, then we will be increasing that cap in case you want to go even higher. Thank you, Dirk. Jacopo asks, when will it be possible to use background noise level and insert noise sources manually? Yes, so this is a part of this sort of STI improvement that's coming in September, that you can, for STI calculations, you can kind of freely control the spectrum of the background noise and things like that to analyze STI performance relating to that. In terms of oralizations, if you want to have background noise in oralizations, then what you would do now is that you have some sources that you have to place some sources into the room that can, and then add like a noise sound to those sources. For example, it can be an HVAC outlet or something like that to get background noises into the oralization. We will be, as we push these kind of improvements of our oralization mechanism over the next coming months, then definitely the ability to add just, not in the simulation, but just in the oralization, like a bit of a background noise level will come as well. I hope that answers the question. Philip asks, when will it be possible to see really single frequencies and not octave bands in the heat maps? Great question. This is so exciting because wave-based methods, can model modal behavior really well. So you can actually analyze the modal behavior of the space really well. We already simulate the whole domain in the wave simulation. So this is more just a question of when do we get it into the UI and the whole back-end piping, to be able to analyze this at the single frequency level. So I think we would say that this is a part of the animation feature here. So later this year, we want to be able that people can see modal behavior at the single frequency level too, and animations of sound over time. Okay, here's an anonymous attendee. First of all, wow. Well, thank you so much for that. Now for my question. I hope it's okay now. But can you explain a little further on the scattering coefficient? Does the default value is the default value good enough to give exact results? So yes. So we have now in the tool one way of entering a scattering coefficient. You enter a single value, a mid-frequency value, and then that's kind of extrapolated to lower and higher frequencies, typically in this sort of S-shaped curve. So if you put in a higher value, then the S curve kind of lifts up and down. Typically at higher frequencies, you have more scattering, and lower frequencies, you have less scattering. This is as mentioned earlier, kind of the industry standard way of modeling scattering, and it works quite well in many cases, although it's of course quite a lot of guesswork in sort of what scattering value to actually put in there. In Treble, with each material, there are default scattering values associated. Those were put in there just to kind of facilitate the workflow, so you wouldn't always have to manually define the scattering coefficient for everything. But I would be mindful of reviewing what scattering coefficients are put in as default, and in many cases I would actually modify them, because scattering is ultimately not really a material property, but it's a geometry property. So you might have a wall which has the material smooth concrete, and that per default has a low scattering coefficient, but maybe this wall has some funky geometric shapes which is made out of smooth concrete, and then I would definitely increase the scattering coefficient. So it's really important to be mindful when assigning the scattering coefficient. It has a huge impact on the results at higher frequencies, or at least a big impact. So yeah, and then as mentioned, just a couple of weeks down the road or so, we will be introducing this ability to input frequency dependent scattering, so you can really play around with this in a more precise manner. Another question from Dirk here. Is the number of rays split when using surface receivers? No, it's the same amount of rays used for the point receivers and the surface receivers. Okay. Follow-up question here. Insert noise sources manually, edited by the user, from Jacobo. So yes, as mentioned earlier, you can certainly place noise sources into the room and use that for oralization or analysis purposes. What's the difference between beam tracing and ray tracing? That's a good question. There's many different variants of beam tracing and ray tracing algorithms, and some of them kind of overlap and so on. There's a great review paper about geometrical acoustics from 2015 by Lauri Savioja and Peter Svensson, which highlights all of this really well. So I can definitely recommend reading that paper. But I would say simply, beam tracing is an accelerated image source method. So it's more deterministic and not stochastic like the ray tracing method. It's great for modeling specular early reflections, and it's much faster than the traditional image source method. Ray tracing is a more stochastic method suited for late reverb measurements, simulations. Scattering value is left out in the wave-based calculations. Good point. Absolutely. Yeah. So wave-based simulations just take scattering inherently into account from the geometry of the room. But that also implies that when you go to high frequencies wave-based, then you need to make sure that there are some geometric details in your model to account for the scattering. Are the benchmark tests with ray tracing also available without mean values of the other products, each individually? Yes, we could share those. So the round-robin providers, they have an Excel sheet essentially on their website where they have all the different tools, the reverberation times of all the different tools that participated in the round-robin. So you can see that there. Okay, Emre asks, can you explain a bit more about this future material generator function? Yes, absolutely. So right now we have a way to import materials into Treble where you can input absorption coefficients, and then we have actually a rather elaborate algorithm that takes those absorption coefficients and converts them to surface impedance kind of in a best guess way. That's pretty fine approach for many cases, although of course it would be preferable to have the impedance in a more precise way, because impedance is a much better characterization of a material than just absorption, energy-based absorption coefficients. The material generator is kind of meant to facilitate this so that you have a little graphic user interface, like a little pop-up, where you would define your own material buildup. For example, let's say you have a perforated panel which has some diameter of holes and some cc distance between holes. It has some thickness, there's some air cavity behind it, and then there's some porous absorber which has some material properties, things like that. And then you input this kind of material buildup, or it can be a gypsum board wall or just a concrete wall or whatever, and then the material generator uses very well established material models for these kinds of buildups to estimate the surface impedance of this particular unique buildup that you have defined. And you can save that as a material and use that in the simulation. So it's a way to reduce the uncertainty we spoke about earlier about material input into room acoustic simulations. Here's a comment from Alex. Thank you for this. Everything's looking great, and I can't wait to get my hands on the API. Really happy to hear that the API is useful for some people. Some other nice comments here. Great webinar, very interesting roadmap. Thumbs up. Thank you, Leonie. Achilles asks, looking forward to the upcoming Rhino integration. Completely agree. That's very exciting. Yeah. We actually have a working prototype of that, so we'll try to push it out as soon as we can. Also, the Python API will enable us to integrate Treble into Acoustics informed form finding algorithms. That's a very good point. Kind of a nice application of being able to integrate the simulation tech into some automated workflows or things like that, Grasshopper and things like that. Here's a question. I wanted to know the average calculation time for simulating a receiver surface. That's a great question. That's indeed something we were really working hard on improving, because our GA solver was, quite acceptable in terms of performance for point receivers. But when we started putting in hundreds or thousands of surface, points on a surface, then we started to see some pretty long calculation times. Right now, it's quite good, I would say. So we saw, for example, the concert hall model here, which had 500 receivers. That's like a pretty dense grid across the whole space, and it took 10 minutes to simulate the whole thing. So it's sort of in that ballpark, but we are definitely working on improving this further and further. We can also really kind of exploit the power of the cloud here, which we haven't really started doing with the surface receivers yet, to do this more in parallel and so on. So we want to bring this down to the seconds range from the minutes range, but it's in the minutes range these days. Here's another question. Is there any option of exporting an arbitrary high order ambisonics order for a spatial impulse response? Great question. So in the web application currently, you can only simulate second order ambisonic impulse responses. Down the road, we will enable more advanced functions in the web application to select different orders. But in the API product that's coming in October, you can already there have, I would say, an arbitrary order. Yes, up to order 16 is what we've been working with so far. Yes, so API product supporting that soon, the web application a bit further down the road. Okay. Few more questions here. I'll keep going for 6 more minutes, and then let's stop it at 30 minutes past here. So is it possible, and how computationally heavy it is, to simulate small mesh geometries, 1 by 1 meter, for example, with multiple small bases? So that's, yeah, you can certainly simulate small geometries and go very high in frequency, like as an example, this room here, which is around 80 cubic meters. We simulated that fully wave-based up to 8 kilohertz, meaning that we needed to use very small mesh elements to do so. And it's it's not a tiny room; it's a medium-sized room. And this was done in, I don't know, something like 10 hours or something like that, using a few GPUs in parallel. And so it depends a bit on, it depends actually a lot on how high in frequency you want to go, how small the mesh elements need to be, and so on. But we're seeing, small rooms, you can do them wave-based only, and it takes some hours, sure, but it's definitely doable. Large rooms, then you kind of do low mid frequencies, and then it's some minutes to maybe a handful of hours, depending on the size of the room, with a wave-based model. Bradley asks, can we see an average reverberation time over custom frequency range in the surface mappings? Great question, great suggestion. Not yet, so it's just per frequency band, but the averaged result will definitely come soon. Philip comments, really very impressive, really excited about it. Thank you, Philip, for the nice comments and questions. Yannick asks, will there be a possibility to do statistic calculations, for example, for reverberation time, or some kind of data export, for example, volume, surface, material data, and areas, in order to compare to the simulation? Yes, this is, so some kind of statistics of the results, for example, across different simulations, across different receivers, and so on. It's a great suggestion. We've talked about it here internally a bit. Haven't fully defined what we want to do in this regard, so we're open to suggestions on what could be most valuable here. But something like this is something we've talked about, but maybe not coming very soon, but yes. Bradley asks, diffraction for GA on the roadmap. Yes, it's on the roadmap, but not coming very soon. I think we want to emphasize the transmission modeling, for example, to begin with. Diffraction is inherently very well modeled in the wave-based part, and our argument is that if you cover the low mid frequencies wave-based, then you're pretty well set for diffraction modeling. But we want to enable GA diffraction as well for high frequencies. So it's on the sort of medium-term roadmap, let's say, maybe sometime next year. And also, Bradley asks if there are some guidelines for scattering definitions. Yes. Well, when we push this new scattering functionality, we will ramp up our documentation around scattering definition and make a tutorial and things like that, because indeed it has a pretty big impact on the simulation results. David asks, what's the main difference between the initial release of the API and the updated release in early 2024? Very good question. So the difference is mainly that the initial release will have a library of directive sound sources that come with it, and not all of the advanced receiver modeling capabilities as well. So when version 2 comes early next year, we want to be able to support any sound source being uploaded to the system, more advanced receiver capabilities, and also more advanced geometry modification and generation capabilities. So it's kind of those three things we'll mostly be working on. Okay. Let's say that this is the last question here. So any plans regarding HRTFs and headphone equalization? Yes, so in the web application, we right now have a standard HRTF, the SATI HRTF. We have actually a working prototype of being able to switch that out for any other HRTF. So that's something that we will want to introduce as a part of our oralization overhaul. I can't say exactly when we will do that, but something that's on the roadmap. Also, maybe incorporating some sort of personalized HRTF technology into that whole chain could be interesting. In the API, you can have any HRTF you want already. And that's on equalization. Yeah, also a great suggestion, something we should look into for sure. All right. Sorry for going 30 minutes over. I see there's some are still here on the line. I really appreciate you staying here. It was very fun presenting this. Thanks for all the great questions. Please write to us on the live chat or drop us an email, write to me on LinkedIn, whatever, if you want to have some follow-up discussions or come with some suggestions. We really want to hear your thoughts and suggestions on what we should be focusing on, and we hope that these new features are of interest. So from all of us at Treble, thanks for today, and see you around. Bye-bye.